In this video, we're going to see how to convert a non-deterministic finite automaton to a deterministic one. We care about this for a couple of reasons. First of all, a non-deterministic automaton is often easier to come up with to describe a language that we're interested in. We don't have to worry about every little detail. But when it comes to actually implementing them, say in a program, we do want determinism because it can be somewhat tricky to do non-deterministic implementations. So we're going to use an example from the previous section 2.1 of a language, and we will see an NFA for it and then convert it to a DFA. The language we're going to use is the set of strings consisting of zeros and one with a one in the third to last position. Here's a regular expression for that. And what that means is that any string in that language will have one of these endings of 3 characters. Now, we already saw a DFA for this language in section 2.1 of the book. Here it is. So as you can see, there are 4 accepting states that track whether it was a 1 in the third to the last position followed by 2 zeros, a 0 and a 1, a 1 and a 0, or a 1 and a 1. Now, if you'll recall this from the previous section, it took a little time to talk about and think about and come up with. You know, it wasn't rocket science by any means, but it turns out that an NFA is much, much easier to come up with most of the time. So let's pretend we hadn't seen that DFA and we want to describe this language. Well, here we have it. 0 plus 1 star, any number of zeros and ones, followed by a 1, and then followed by either a 0 or a 1 2 times, and then we quit right here. So this NFA more directly resembles the language or mirrors what the language is, but it is non-deterministic. Why? Well, one example is that if you look at state 0, when you read a 1, you have 2 choices. You can stay in state 0 or you can go to state 1. And at the end state, which I'm calling one question, you can't go anywhere. You got to stop there. So in other words, for this particular NFA to recognize a valid string, you have to make that transition from state 0 to state 1 at just the right moment. So that's the source of the non-determinism. The way that we're going to convert this to a DFA is track all of the possibilities at once. Whenever we see multiple outputs for the same input character from a particular state, we will record those as a set, and that will become a state in the DFA. And that state will model the fact that it is representing 2 states from the original NFA. So I like to call those a composite state, whatever you want to call them, but that's why it's called subset construction, is because we will have a set of states that we have reached. Sometimes it'll be a singleton, sometimes it could be an empty set, but often it will be multiple sets because of the non-determinism. Now, in order to construct this DFA, what we're going to do is use a transition table, and we're going to construct it a little bit at a time, starting with the start state of the NFA. So here I have reproduced the drawing. Getting rid of the question marks, I found those a little unwieldy, so I used an X instead. But that's not important. The start state of the DFA will be the start state of the NFA. And now what we do is we will ask ourselves, where can we go from state 0 with the various inputs, a 0 and a 1? And of course, the answer for 0 is we'll just stay right in state 0. And when we read a 1, though, we actually have 2 choices. And so here we have to put 0 and 1, and then we will put them together as a set, like this. So that now becomes a set but we're going to track its behavior, recalling that it's really modeling states 0 and 1 at the same time. Now I'm going to add that to my list of states on the left and then repeat the process. I'm going to say, where does that take me with the different inputs? To do that, I'm going to look at each individual state that is inside of the composite state and then combine the results of where I can go. So with state 0, when reading a 0, I will clearly go back to 0, so that will be part of the result that I will place. But when I'm in state 1 and I get a 0, I move to state 1x. And so I'm going to put a 1 and an x in that spot. And then likewise for reading a 1, what I will do is I will say, well, when I read a 1, I'm going to have a 0 and a 1 and a 1x. And so I end up with this. Now, these new states that I have reached, these composite states, are being seen for the first time in the table, so I will add them and process them as well. So it's just a process of beginning with the start state and deciding where can we go, but simultaneously tracking states where there are multiple choices. And so now we'll continue the process. Where can I go from 0 and 1x with a 0 and a 1 as input, and then add those results? And that takes us to here. So the answer is I can go here with a 0 from 0 and 1x, and I can go here from 0 and 1x with a 1. And I need to add those two states again, as usual. So the process is getting to be pretty familiar now, so we'll just continue on. Let's fill in these blanks. So when we fill in those blanks, we'll see these states, and they are also new. We haven't seen those combinations just yet, so I will add those as well. So continuing the process, we get to this point. And it is interesting to note that when I'm in a 0 and I get a 0, of course, I cycle on the 0. When I am in 1xx, I don't go anywhere, so that does not contribute to the movement. All I can do is do that. And that reflects the fact that we did the same thing in the DFA. There was an arrow from a particular state back to the start state 0 in the DFA. So again, we're tracking all of the possible behavior in this resulting DFA. Now, I need to fill in the blanks for these last two new states, which I got from this line. Let's see, these right here. Yeah, those right here, which appear here. Let's process those. When we do that, we'll notice that these states already exist in the left-hand column in the list of states. So I am finished with looking at all the possible traversals starting at the start state in this machine. And so I don't have to continue this process anymore. I now have something from which I can draw a transition graph if I desire, but this is good enough for representing the DFA. There's no non-determinism here. There's no choice on what to do. And every composite state has been tracked according to its behavior, so I'm missing nothing. The only thing left to do is to decide which states are accepting states. The answer to that is any composite state that contains an original accepting state from the NFA. And 1xx was the last state in our case, and so these four states will be accepting. And that actually is quite reminiscent of what we saw in the original DFA. There were four accepting states, one which was tracking 100 and 101 and 110 and 111. So now we can draw, if we like, we can draw the DFA, and in this case it's going to look strikingly familiar. The transition graph for this DFA in the table on the left is identical to the one we had in the beginning from the previous section in the book. Only the state names have changed. But that's not important. Now, the reason I bring this up is because this is not always the case when you convert an NFA to a DFA, meaning that sometimes you will have redundant states. That is, we can perhaps get rid of a state and still have the same DFA, that is, accept the same language. Now, we haven't covered that yet. That's in the next section, 2.3. I just want to alert you to that if you already have a DFA, but then you take an NFA for it and convert it to a DFA, you may not get an isomorphic graph. It just depends on what DFA you started with. But if you did have a minimal DFA, you may or may not get it. You still may have to minimize that DFA you got from the conversion process. But in any case, we're at the end of this example.